Good afternoon, this is Dr. Bailey for CHEM108 on our snow day. I hope you guys are all staying safe and enjoying a little bit of time outside of school. So that we don't fall behind this semester, I wanted to make sure to record what we were going to talk about today in class, since we have an exam a week from yesterday on the 20th of March. We're going to have a bit of kinetics on that, so I figured that this would help set you guys up for that. So the objectives for this class are going to be for you guys to follow along with the worksheet. The worksheet is attached to the announcement I sent out. It's also Canvas under Files for Week 6 Kinetics. Please make sure to download that worksheet so that you are working along. When I ask you to pause in this video, please make sure to do that. Take the time to work through this on yourself. Remember, you learn much less when you just listen to someone else talking about something versus doing it on your own, thinking through it, trying to see how you would approach it, and then coming back together and figuring out how to do this. I'd also suggest working with someone else. So if you can find someone else that lives on your hall or close by, try to ask them if they're willing to come and meet with you. So for today's video class, my goal is for you guys to be able to talk about kinetics, and that means to describe how fast a reaction occurs, and also to then be a bit more specific and determine the average and compare that to the instantaneous rates of consumption of reactants, production of products, and the rate of the entire reaction, which relates to both of those above. So to start out, we're going to have to just talk big picture about what kinetics even is. And we've talked about chemical reactions in first semester, but this semester, when we get into kinetics, we're going to be talking about chemical reactions do occur. For instance, ethanol gets metabolized to be excreted from our body. And so if someone drinks an alcoholic beverage, or in this case 2 drinks, what we're going to be talking about is not necessarily the rate of absorption, which is when that drug gets entered into our stomach, it ends up getting put into our bloodstream, and this is showing the blood concentration of ethanol. So once we have this peak up here, we're going to describe, well, how do we predict how long it will take for that to be removed from our body? How long will it be present in our body? What is this time frame? And then how long until you're below an acceptable level where you can get behind the wheel and drive without being considered legally intoxicated? There's plenty of other examples as well. So one that we've seen about recently in the news in the last couple of years is Fukushima. This is when the tsunami first hit Fukushima. And as you guys probably know, there was a nuclear power plant there, and it was devastating how that power plant got hit. So there's multiple reactors that had cracks and ended up overheating, and so that resulted in the release of a lot of radioactive material. Now, radioactive material isn't going to be there forever. It disintegrates over time. It releases particles that allow decomposition, and when we say how long is it until it's safe to go back there, we can say, well, this is what we started out at 100%. And then with radioactivity, it's always going to decay, where it's going to go from the initial concentration to half that concentration in a given amount of time, half that concentration again in the same amount of time, and each of these, so for radioactivity, we can predict very well how long it will take until something is no longer radioactive, or how much radioactivity is left, by looking at half-lives. Something that I worked with earlier in my career in biomedical research was how to identify where a tumor might exist in an animal, was our model, and then extrapolate. If we can find an imaging agent, we should be able to take that and use it in human patients in order to identify where a tumor would be when it's spread throughout the body. And normally we would just try to figure out where these tumors were, and we'd probably only identify the main mass of the tumor, and we wouldn't necessarily be able to find the metastases. And so imaging agents like this that emit light, fluorescent imaging agents, they have a certain amount of time that they fluoresce, and so we can look at how long after you inject a fluorescent agent will it be until you no longer can see light being emitted from that. So what I want you guys to do is, on the worksheet, you have this blank graph. And what we're going to be talking about is that you have a chemical reaction where a chemical A is our starting material, B is our product, and we're going to say, well, how does that change over time? So I want us to start drawing on this graph by saying we have 40 of these black A's starting off with, and those are 40 starting materials. So we're going to say we're starting with all of A, and we have 0 of B down here. What could this graph look like over time as we move forward in time and we have the chemical reaction shown here? So go ahead, pause for a second, and I want you guys to now draw what the graph is going to look like. Maybe it's going to look like this. Maybe it's going to look like this. Whatever it's going to be, go ahead and draw what you predict that graph to be. Go ahead and pause. I'm going to pause while you go ahead and do that. And now, as you guys finish, I'm going to try to get this to continue. You're in drawing mode. So, what I want to talk about is what these lines are going to look like. We started with all black and no red, and then as we progressed over time, we ended up generating more and more of B, and less of A were present. So what we're going to be talking about is how does the amount of A relate to B at each of these time points? What is the stoichiometric ratio between those? And then how does that also relate to the rate, which is the change in number of molecules over time, or really the change in concentration over the change in time. So we can talk about that from point 0 to 10 seconds, or we can talk about from 0 to the end of the reaction. A lot of different ways we can talk about that. So here's another chemical reaction that we're going to be looking at a couple times throughout the semester when we're talking about equilibrium versus kinetics. And if we have this reaction, if we start with all A and B, and over time those guys get used up, and they're producing C, which is the pink line. But at a certain point, that reaction slows down, and it ends up generating a very constant concentration, where these concentrations, you can see that there's no change in concentration, and hence the flat lines exist there. Does that mean that the reaction stops, or what's happening? And you guys have already been to 2 workshops up until now, where you should be able to answer that question. So write down your thoughts. Does that reaction stop, or what's happening? And so the part of this graph that refers to kinetics is going to be this left side, when we're having a change in the overall concentration because the reaction is proceeding in the forward direction. And on the right side, this is what's called the equilibrium concentration, the equilibrium part of any reaction. And as you guys know from workshop, the reaction doesn't stop on the right side, but the rate at which the products are generated from reactants is equal to the rate at which the products will generate reactants. And so the forward and reverse reaction are happening at the same rate. So there's still A and B becoming C, and C becoming A and B, and those are happening at the same rate. So we see no net change in concentration of any of the reactants in equilibrium phase. In kinetic phase, we see an absolute change in the concentration, and that's because the forward and reverse reaction are not happening at the same rate. So we have the kinetic phase and equilibrium phase of the graph. We're looking on the left side at reaction rate and the mechanism, and then on the right side, we're looking at what is the equilibrium concentration that is reached. So knowing what concentrations of each of these we end up with tells us something about that reaction, and that allows us to predict in future reactions what concentrations we're likely to have. Another way to say this is on the left of this graph, that reaction is not at equilibrium, meaning that Gibbs free energy is not equal to 0. Or at equilibrium, when the reaction is not proceeding forward or backward, that reaction is at equilibrium, and Gibbs free energy is hence at 0. So some of the reactions that our book highlights, which I highly recommend you go and read in chapter 14, is related to air quality. So there's a lot of laws in place that keep air from being polluted, but in certain cities, even with all those regulations, we still end up with a huge amount of smog pollution. So this is a picture of Salt Lake City, and I got the fortune of visiting there last spring. And as I flew in to the airport, it's in the middle of this big valley where there's just giant mountains on both sides, and it was crazy. You couldn't even see the ground as we were approaching on the plane. And it turns out that when the air is really still, that there's a lot of factories in that valley that produce a ton of smog, and that comes from cars as well. And those coal-burning fire plants, as well as all the cars, generate the smog so that you can't actually see across the valley. And as the plane lands, you can't actually see the runway. So on the left side here is a picture of a high smog day, and on the right side is when it's clear and the wind is actually blowing all that smog out. So we're going to be talking about the chemical reactions, and the book does as well, that lead to this kind of smog in the atmosphere. And here's a picture kind of zoomed out. So the chemicals we're going to be looking at are nitrogen gas, which is 78% of all the air molecules. And that's relevant because oxygen gas, which is 20% of all the gas molecules, when our combustion engines take that in, so our car takes in air in order to burn the oxygen with gasoline, or a coal-burning fire plant does the same. It doesn't discriminate which gas it takes in both. Under combustion reactions, this one is the main reactant that we're looking for, but it also does happen to react with nitrogen gas. And when that does, we end up generating nitrogen monoxide, nitrogen dioxide, ozone, and then some other pretty nasty chemicals. So we're going to be talking about those reactions. And if you look over the course of a day, here's the very early morning on the left side, and then these volatile organic compounds, which means these are compounds that are airborne, that have carbon in them, which is related to some of these other reactions. Why do you think it is that NO spikes at 7 a.m.? Talk to your neighbor and write down your thoughts. And then if we notice, NO2 spikes at about 10 a.m. And then ozone doesn't spike until many, many hours later. So we're going to be talking about how the generation of NO from N2 and O2 in a combustion engine, then over time will generate NO2, and then NO2 over time can generate some ozone as well. So these stepwise reactions are going to be something that we're discussing here. So that first reaction I was talking about, the inside of a car's engine, it doesn't discriminate. It pulls in nitrogen gas N2 and oxygen gas O2. And while the main reaction for O2 is combustion with our gasoline, a side reaction that happens at those really high temperatures inside of a gas cylinder is that those two gases react directly with each other, and they generate this nasty byproduct, part of smog, called nitrogen monoxide. So pause for a second and get situated with this table. Look at what information is being shown here in this table. So this is a trial, a chemical reaction where they isolated nitrogen and oxygen gas. And they started at equal concentrations. And while that's not exactly what we do have when we are burning inside of an engine, we said that we actually have about 4 times as much N2 as O2. They're starting at time 0 with 17 micromolar concentration of both of these. And yes, they're referring to micromolar. It's the number of moles per liter of solution, and the solution is a gas in this case. And then they're saying, well, we start with none of this product. As we go forward in time, which is down, we're consuming our reactants, and then we are converting those into products. So the questions I want you to ask yourself is, why does the concentration of N2 and O2 go down by the same amount each time? They don't even get two separate columns for these. I hope you guys notice that the stoichiometric coefficients for both of these are equal. And what I really need you guys to say is that for every 1 mole of nitrogen gas that's used, 1 mole of oxygen gas is also used. And in that process, we're going to generate 2 moles of nitrogen monoxide. Now that stoichiometric ratio is going to be critical moving forward that we pay attention to, and we're able to say that as a sentence. So in class on Thursday, I'm going to ask you guys to say in a sentence how that stoichiometric ratio tells us that when 1 mole of nitrogen is consumed, 1 mole of O2 is consumed, and we produce 2 moles of NO. And that's really important because that's during that same time frame where 1 mole and 1 mole are used, we generate 2, and that is going to give us a relation that we can talk about in terms of rate. During the time that we use 1 mole of N2, that same time we're going to make 2 moles of NO, and we're also going to use 1 mole of O2. And so that, remember, if we go back to rate, is equal to the change in concentration of something during a certain period of time, or a change in time. So that sentence is going to be critical. So during this first step here, it looks like we decreased our concentration by, 3.9 micromolar. So then pause for a second and ask your neighbor why it is we generate 7.8 micromolar of that product. I hope you guys see that 3.9 micromolar, during the time we used up that much N2 and O2, we generated twice as much of the NO, which is 7.8 micromolar. And you can do the whole thing, the same thing, every one of these steps on the way down, that whatever the change is, so if we look at the change here during this last one, this is 0.9 is the change, and then here we see a change that's approximately double that concentration change. So that's 1.9, which based on our sig figs here, we couldn't really say whether it was 1.8 or 1.9. There might be a little bit more going on there. So let's keep that in mind, that the stoichiometric ratio between our reactants and each other, one reactant to the other, as well as reactants to products, allows us to predict the rate of production of the products if we know the rate of consumption of the reactants. And instead of looking at this in graphical format, or in a table, we can look at this as a graph. So I want you in a second to pause, and I want you to say, well, how do we describe the rate of consumption of our reactants and the rate of production of products in a graphical format? Go ahead and pause, think about that, or talk to your classmate, hopefully you're sitting next to. So imagine that there's 2 ways that you guys talk about this, and I am being very serious. I want you guys to pause and think about this and write down your thoughts or talk to someone else. Remember, listening to me isn't a very effective way to learn. So the 2 ways are, we said the rate is change in concentration over change in time. So if we're talking about the consumption of N2, we can say, okay, here is the change in, if we go from data point 1 to data point 2, change in concentration is that, change in time is that. So we could find those 2 data points and then find the change in y, which is concentration, the change in x. So in this case, rate equals change in y, which is change in concentration, over change in x, and that's the same thing as our rate. We can do the same thing for the production of our product. We can say from time point 0 to time point 5 seconds. So rate of product is, we have 5 seconds on the bottom because that's the change in time. Change in concentration, it looks like we gained 7.5 micromolar. And so we can do this for any 2 points of time on this. And it turns out that that's not the most accurate way, as we'll come talk to in a second. This is going to be probably pretty bad. And we try to say, At 15 seconds, if we wanted to know the change in concentration or the change in time there, it would actually be much more effective to actually draw a tangent line on there and say what's the slope of that tangent line, because that's the instantaneous rate of change. Okay, so we've talked a lot about this reaction where we start with N2 and O2 and we're generating NO. So let's take a look at the next reaction. The next reaction is where that nitrogen monoxide is a reactive species. It's actually a radical species. That is now going to react with oxygen gas. And it still does that at very high temperatures inside the engine. Actually, I'm wrong. That reaction happens outside of the engine, which is why it happens at a later time. So, if we take a look here, go ahead and pause and try to interpret the data here. So after you've paused, we're going to orient ourselves again and say that as time increases, if we start with only our reactants, right, our reactants here, that over time we start with 0 and we're going to generate the product. Now let's pay really close attention here. Before, the change in both of our reactants, concentration was the same. Is that occurring again? Well, look, let's go through the first time point, 285 seconds. Our concentration of NO decreases by 0.001 molar. But the concentration of our O2 only decreases by half that amount. Why is that? Hopefully you guys are pointing out the stoichiometric coefficients are different. So I want you to write down in a sentence what the stoichiometric relations of these tell us, or how we can use a sentence to describe the relative rate of consumption of each of those and production of the product. Go ahead and pause and try to write that down or talk that through with your neighbor. Okay, so the way that I would say that would be that during the time when 2 moles of NO gas are consumed, 1 mole of O2 is also consumed. So that 2-to-1 ratio can be seen here. And during that time, we also will generate 2 moles of NO. So that 2-to-1-to-2 ratio will show that the change in product concentration should be the same, because the same stoichiometric coefficient is there, between our reactant of NO and our product of NO2. And we should be able to do that all the way down, and notice that each one of these changes is the same change over here, and that oxygen changes by half as much during every one of these steps. So let's take a look at that in a graphic format. So I want you to look at these, this graphic representation, and there's our equation, our balanced equation up above again, and I want you to think about and click in, aka circle, on your worksheet, which one of these lines represents the formation of NO2. And I want you to describe why. Go ahead and pause, decide which one, and then give a good justification for why. So we have 3 to choose from, and the question is, what is going to be the most different about NO2? And I hope you guys are saying, well, we make the product. So what's going to happen to the concentration of product over time? That means it's going to go up. So there's only one of these graphs that is we're generating the product, and that is C. So over time, concentration of the orange line goes up over time. Okay, so that was the easy question. The difficult question then becomes, which one of these 2 graphs represents the consumption of O2? Go ahead and pause, make sure that you can answer which one, and really dig down into why you decided A or B. So if we're looking at both of these, we can say for sure we know it's not C, because that is increasing and our reactant concentrations are always going down. And a lot of times this can be quite tricky to decide. But if we go back to that sentence way that I want you guys to work through this, if we say that during the time that 2 NO are being consumed, only 1 O2 is being consumed. Which one is being consumed faster? Which one should be going away at a higher rate? the one where 2 go away in the same time frame is only 1 over here. That means that 2 is going to go away much faster. So that means that our A has to be O2 because it's disappearing, it's being consumed at half the rate of B, and therefore B has to be the concentration of NO gas. So that is the hardest part of the beginning of kinetics, and this will definitely be on exam 1. So try to talk through that for every example that we come up to. And then I think we got to that point there. So then let's look at this same graph that we just had up. If you wanted to describe the initial rate of this reaction, which time frame would you study? Pause for a second and decide which one of the answers you think is best. So let's go back to our definition of rate. It is the change in concentration over the change in time. So the question that really comes out here is, does the rate change over the course of this reaction? And I kind of gave a little hint earlier when we talked about the instantaneous rate of change is actually the most accurate way of describing. So if we were to drive the instantaneous rate of change of this reaction, we would probably look at either the reactants or the product, and they're going to be related as we'll talk about soon. And we would say, well, that rate of change is very different than if we just looked at the average over the course of the entire reaction, which is that third line that I drew there. Looking at the slope of those, you can tell there's a very big difference. However, you could also be very observant and say, well, all those lines that you could draw as the tangent at time 0 would be different as well. And how do those relate? Which one do we use to say is the initial rate of the reaction? So going forward, we're going to come back to that question, but we're going to say that unless we know the tangent line and we can do that, we're going to focus in on the closest thing we can to the tangent line. In this case, it's from time 0 to 285 seconds. And we could say the initial rate of consumption of NO, the consumption of O2, would be found by looking at the change in concentration over the change in time. Or the initial rate of production of NO2, we would also use those first 2 time points. We are not going to use the entire thing, because that tells us, well, how long until we stopped measuring, and how fast did it consume on average for a much longer period of time. But if we're talking about the initial rate, that tells us about, well, we know how much we started with. If we have those initial concentrations, what is going to be the change in the concentration over time, or the rate of the reaction, initial rate of the reaction? So let's go ahead and look at some options here. Some ways to work with this. So we first said that to find the initial rate of consumption of O2, we would use the first 2 time points, and we would say, well, what's the change in concentration over the change in time? So that's what we have here, that the change in time is 285 seconds. That's what we said on the right side here. And the change in concentration is looking at the difference between the first 2 time points of this concentration. The next question is, it looks like I have some updates that need to be closed. Apologize for that. The next question is going to be, well, how does that calculation, how can that relate to the initial rate of consumption of NO? So we have our balanced chemical equation. Go ahead and pause and try to decide which one of these would be the initial rate of consumption of our other reactant, NO. So if we look over those, we can do one of 2 things. We can actually look at between 0 and 285 seconds and the change in concentration here. That's totally fine and completely doable. What I want you guys to think about is how can we, without the table, if we only had the change in concentration of oxygen over the change in time, how could we use that to answer this question? So let's go back here. If oxygen is only being consumed for 1 mole of oxygen, we at the same time need 2 moles of NO, that means that it's going to be consumed 2 times faster than O2 is consumed. So which one of these is being consumed twice as fast? So we would do the initial rate of consumption of oxygen times 2, and that gives us about 3.6 times 10 to the negative 6 molar. And if we were to go back and do some calculations and didn't worry about sig fig so much, we would find that this is the best answer. And now what do you notice about the sign of the rate? We have a negative. So what does the negative tell us? And I hope you guys are looking at that. The concentration is going down for both of these, and for the product it's going up. So that's a way we could say, without even saying what's the rate of reaction for O2, we could have just said negative 1.8, and that tells us it's being consumed and it is a reactant. Okay, so now go ahead and do the same thing for the initial rate of production of NO2, and be careful with your sign. So after you go through, hopefully we can do our logic way instead of simply looking at the actual data. We can say that I know the rate of consumption of NO is equal to the rate of production of NO2 because their stoichiometric coefficients are the same. So now the question is it negative 3.5 times 10 to the negative 6 molar per second, or 3.5? And because it is rate of production, it would be a positive sign, and hence D would be the right answer. So now, all of these different numbers are different. So if I want to say, well, how fast is this reaction happening? None of these numbers can really be used because they're all different because of the different stoichiometric coefficients. So I want you to go ahead and click in what you think is going to be defined as the initial rate of this reaction. Go ahead and pause. And what I want us to think about is, this is the initial rate of reaction. Why is that? I really urge you guys to read a little bit in chapter 14 before you come to class on Thursday. But what we're trying to get at is that in order to describe the rate of a reaction, it has to be some number that's independent of one reactant versus another reactant versus the product. It has to be the most simplified version of describing how all those reactants and products are being consumed in one single number. So basically what we're doing is we're saying, well, what would the rate be if we had a coefficient of 1? In this case, we actually do have one reactant with a coefficient of 1, right? Oxygen has a coefficient of 1. So that makes this simpler for this problem. But this definition of the reaction rate applies to any reaction. And because we've said that the reaction scales appropriately based on the stoichiometric coefficient, you'll see in a minute why it is that we'll always refer to the rate of reaction as if, what would the rate be if something had a coefficient of 1? The last thing is, what do you guys notice about the sign of the rate of the reaction? And so we're always going to be saying that the rate of reaction is a positive number. It always talks about, you can relate it to, well, if that's the rate of reaction, then the rate of consumption of O2 is going to be negative, and the coefficient is 1, so it's going to be the same as rate of reaction. I can also use that to say, well, the rate of consumption of NO is going to be twice, because there's a 2 for stoichiometric coefficient, and it's going to be negative because it's consuming. Or the rate of production of NO2 would be 2 times the rate of reaction, and it's a positive sign because it's producing. So now let's take a look at a chemical reaction that is used for hydrogen fuel cells, as well as some cars that actually drive straight on hydrogen gas. It's pretty cool. We can actually take hydrogen gas, and when we combine it with oxygen gas, we burn it, and the only byproduct is water. although there are some smog and other products as well because we don't use just straight oxygen to burn it. So here's a chemical reaction, the balanced chemical reaction. You guys know this from first semester. Hydrogen gas combines with oxygen gas to generate water, and those stoichiometric coefficients, once again, are very important. So our rate of reaction, and I don't know actually if this is where I wanted it to show. I think there's a clicker question that's going to show up. So if you can, just look at the question itself. When the concentration of O2, one of our reactants, is decreasing at 0.23 moles per liter second, or molar per second, what is the rate at which water concentration is increasing? Go ahead and pause and try to work through it, and I've given you some hints here in these animations that showed up too early. Go ahead and say in a sentence how the rate of consumption of O2 relates to the rate of production of water. I'm hoping you guys are saying that for every one, in the time that 1 mole of oxygen is consumed, twice as much water is produced. And remember, because rate equals the change in concentration over the change in time, we're saying that the change in time is the same for both, but water has twice as much of a change in concentration, meaning that the rate also has to be twice as much. So the rate of reaction, we could say, is equal to the rate of consumption of O2, because that would be our stoichiometric coefficient of 1. So the rate of production of water, then, has to be twice. So let's see if I can get this here. So in other words, the rate of production of water is 2 times the rate of consumption of oxygen. And that's 0.4346 molar per second. Let's take a look at one last example here. And this example is going to be a bit more challenging. So if I give you the rate of consumption of A, it's listed here, go ahead and try to decide whether E is being produced at a faster or slower rate than A. And don't think too much about the signs here. I want to know that as A goes away, is E being generated at the same rate, a faster rate, or a slower rate? Go ahead and pause, determine which is your answer. I'm really expecting you guys now, after watching 37 minutes of this, to be starting to talk through this in a sentence. So during the same time that 3A are consumed, 2B are also consumed. So it's consumed at a slower rate because there's only 2 in the same time as 3 of A. But also during that time that 3A are consumed, 4D are produced, and 5E are produced. So 5 being produced in the same time is greater than 3 being produced in that same amount of time. So that means that E is being produced faster than A is consumed. So let's go ahead and calculate that. I want you guys to calculate the rate of production of E at this time. So we know the rate of consumption is negative 5.7 times 10 to the negative 4th molar per second for A. Go ahead and figure out what the rate of production of E is. Go ahead and make sure you're paused, work through this. And I'm going to say the easiest way to answer this question is not to convert directly from one to the other. I'm going to say that instead we're going to do an intermediate step. And we're going to find the rate of reaction. And remember I said that's as if we had a stoichiometric coefficient of 1. So we know that that would be, A would be consumed 3 times greater than the rate of reaction. So that means that the rate of reaction, I'm going to do RxN for reaction, is equal to the rate of consumption of A. We're going to divide that by 3. And that is going to be the rate of the whole reaction if we have that as a positive sign. I'll grab my calculator here. I'm going to say 5.7 times 10 to the negative 4th divided by 3 is 1.9 times 10 to the negative 4th molar per second. That's our rate of reaction. And that's awesome because now, if we want to find the rate of production of any of these, we can just say, well, I know that 5E are produced in the same time as 3A, so that means that E is being produced at 5 times the rate of the reaction. So this generic rate of reaction is something as a multiplier. We can multiply out from that in order to determine the rate of consumption or production of any of the other things. So that means the rate of production of E is equal to 5 times the rate of the reaction. So that means 5 times 1.9 times 10 to the negative 4th, which is 9.5 times 10 to the negative 4th molar per second. You guys follow that? And yes, your book gives you the mathematical representation of that, and you can do 5/3 the speed. It would do the same thing as what we just did. It basically says that the change in concentration of A, the rate of A, divided by 3, that's the rate of reaction. And then we're saying the rate of reaction times 5, now that's the rate of production of E. I think that this is much more straightforward if you just find the rate of reaction first, and then second thing you do is multiply by stoichiometric coefficient to find what you're looking for. And you can find the rate of consumption of B if you wanted through that. You could find the rate of production of D or the rate of production of E. Any of them, they all relate through that initial, or through that rate of the reaction, that generic term, this rate of reaction. So I hope that in this video that you guys took the time and worked through these problems on your own, and now you can describe how fast the reaction occurs and determine the average or instantaneous rate of the consumption of reactants, production of products, or the entire reaction, that rate of reaction, and you can do that all through the stoichiometric coefficients. I'll see you guys in class on Thursday. Don't forget about the pre-class quiz for Thursday. Thanks.